Good morning, everybody. I'm Antonio Edoardo Bargellini, and today I'm going to present a joint work done with Professor Giulia Spaletta and Professor Daniele Vitelli. And the title of this presentation is Extended Logistic Type Equation in Socio-economic Growth Modeling. Indeed, what we have done is to study an economic growth model, which is a well-known growth model, in which what we've done is to try to give a more realistic structure to the labor force. And we were able to find, as we will see, some exact solutions in terms of hypergeometric functions. And in some other cases, we were able to find some bounding solutions for the model we are considering. So I start with a background about the model. We consider a very famous model, the neoclassical growth theory, which is the Solos-1 model, in which the output of a country or an economy is defined as the equation you see above, which is a composition of three components, which is the technical progress, the capital, and the labor force. And in particular, we model a Cobb-Douglas production function in which the exponent lies between is inside the interval 0, 1. And the standard model considers a population dynamics, labor force dynamics, which is exponential in the end, because it is the classical Malthusian population dynamics, which is the second formula you see here. And clearly, considering this type of evolution of the population and inserting inside the equation 1, which is the equation that models the ratio between capital over labor, which is also called capital intensity, Solo was able to find an exact solutions. And the point is that this model has some drawbacks in the sense that considering a labor force that evolves exponentially is not very realistic, because the labor force, especially in the Western countries, has like a bound. They have an upper bound, so they are limited, and they cannot grow exponentially. And so, since there are these drawbacks, there is a stream of literature that considers some extension of this model. In particular, we start with Dangan, which insert inside the evolution of the labor force a logistic law that has a bounds that models a labor force that cannot grow exponentially. And it was not able to find a closed force solution that was eventually found by Mingari and Vitelli, who were able to find an exact solution for this type of model, so with the logistic law, in terms of the hypergeometric function. And based on this result, Brito and Maldonado extended it, considering another type of model, in particular the von Bertalanffy population dynamics, which is a differential equation that is very used in biology, for instance, to model the evolution of cells of cancers, but also in biology to model the population of fish. And they were able to find a closed force solution, because von Bertalanffy equation is pretty much like a logistic type equation. And what we've done is to try to extend this type of model, trying to make it more reliable and more realistic, and to obtain a greater realism and flexibility. And here I recall the integral representation theorem for the Gauss hypergeometric function, because this formula will be used later on in order to compute the exact solution. So the classical von Bertalanffy model is the one that you see here at the bottom of the slides. That is a differential equation with respect to time, in which we have the parameter r, which controls the speed at which the population reaches L infinity, L infinity is the carrying capacity, so it represents the limit after which the population cannot grow anymore. Then it has a negative penalty that considers the population, that takes into account what? The fact that that clearly the population needs to reach the carrying capacity, but as long as the population reaches the carrying capacity, the speed at which this grows starts to decay. Okay, so very, very much similar to the logistic equation. And the first thing that we've done, so in the constant parameter model, what we've done to split this equation considering two different types of parameters, one multiplying the carrying capacity and the other one multiplying the negative term. And in the second case, what we've done is to model with a coefficient that depends on time, exactly the coefficient that multiplies the carrying capacity, trying to find again some exact solution for this type of situations. So for the first case, we have again the form Bertalanffy equation is a linear ODE, so it has a closed form solution. And for the first case, the solution is the one that you see here in the bottom of the slide. Is very much similar to the von Bertalanffy equation, the classical one, since the limit as t goes to infinity kills exactly the second term of the solution, so it remains only the first term. But the only difference with the classical von Bertalanffy model is that we have the ratio between R1 and R2. Here we impose that R1 is greater than R2 in order to maintain the fact that the new carrying capacity is at least bigger than, at least similar to the older carrying capacity. But this is the ratio between these two parameters is very important, because what we have is that we have a new carrying capacity, which is exactly the ratio between R1 and R2 times L infinity. And we proceed similar to the results. We do the work of Brito and Maldonado, so we compute the logarithmic derivative of this equation, which is the rate nu of t, which is actually the rate at which population grows. And then we insert it inside the capital density model, which is a Bernoulli equation that can be linearized using this change of variables. So setting u equal to k over to 1 minus alpha. And linearizing it, we get a linear ODE that has an integral solution that is a closed form solution. And the only thing that you have to compute is the last integral that you see, which is the integral from 0 to t of e2 minus h of tau in the tau. H of tau is computed by solving this integral, which is an elementary integral. So what we are left with computing is the integral to e2 minus h of tau. And here comes into place the integral representation theorem and the solutions in terms of hypergeometric function, because in order to express in order to use the integral representation theorem, what you have to do is to change the variable inside the integral, so setting p equal to er2 times tau. And then we get an integral that starts from that, which has the lower as a lower bound 1 and as upper bound e to r2 times t. And then in order to use the integral representation theorem, we split the domain of integration. So we consider an integral starting from 0 ending to the er2 times t, and the second minus a second integral starting from 0 and ending to 1. So the second integral can be used directly. It is using the integral representation theorem, and it is called as I of 0. While the second integral must be simply standardized, and it is I of t. So the difference between the two, multiplying by the constant term at the beginning, gives us the exact solution for the integral that we were looking for, and then we simply insert back inside the equation, and we get the exact solution in terms of u. And since we have just changed the variable, we elevate everything to 1 over 1 minus alpha, and we get the solutions in terms of k, or of little k. So according to this model, we were able to find an exact solution for the equation. Unfortunately, we cannot say the same thing for the time varying parameter, because in particular what we've done is to, following a stream of literature that deals with seasonal growth, in particular seasonal growth related to population of fish, we have seen that in the von Bertalanffy equation was also used considering time-dependent coefficient, in particular periodic coefficient that models exactly the seasonality of a population dynamic. And so we used we decided to use the same idea, in particular because we are modeling the labor force. So the seasonality, for instance, means that we have periods of higher use of labor force because we have periods of in which the output of a country is high, so people are we have much more employment and periods of unemployment. So what we chose for the time-dependent coefficient of RT is the one that you see here, which is a combination of the previous constant parameters summed to a periodic function that has two parameters, which is B is the amplitude, which means how much, for instance, the cyclical element can have an impact on the labor force, and while the frequency means how often for instance, periods of employment or unemployment can occur. And the situation is very similar. So the solution for this new von Bertalanffy equation can be found, and it is the one you see here that depends on the function big G of t, which is written below. That depends also on the function little g of t, and this function is very important because it will be used later on in order to compute the exact solution. And we proceed very similar to before. So what we just do is to simply compute the logarithmic derivative of this equation, which is nu of t, and then insert back inside the capital density equation, which I wrote here. And here it is already the linearized equation, which has a closed form solution, as we know, since it is a linear ODE. The problem here is, again, to at the end of the day, to solve the last integral, so z of t. But in this case, since we have the presence of this periodic function, there cannot be any closed form solutions or solution for this specific in this case. So what we do is, what we've done is to, since inside of big G of t there is the function little g of t, that is a composition of two periodic functions. So it is a bounded function, and it admits a minimum and a maximum in the interval 0t. We decided to find the minimum and the maximum, and to insert back in place of g of t the minimum in one case and the maximum in the other case. In particular, the minimum and the maximum in this case are minus square root of p and square root of p, since they're also symmetric. And we proceed in the same very similar way as before. So what we've done is to consider again the interval starting from 0 up to t. Then we change the variable. We split the domain of integration, and since we can use again the integral representation theorem, what we get is again a solution in terms of hypergeometric function. And so the idea was to try to find an upper and a lower bound for the theoretical solution that lies between the two. And after doing so, we test with Mathematica using and this also using a numerical solution if also numerically we have that the numerical solution lies between the up and the lower bound. So it is exactly what we've done, and we also test all the other models still with Mathematica. And so we developed everything in Mathematica. We've done some simulations in order to assess also how some sensitivity analysis on the parameter, if they are consistent with the economic theory and so on. And we've done also comparative plots in order to see if, especially for the last case, if the numerical solution is exactly inside the bounds. So this is the first model, so the constant parameter model. In particular, I plot the evolution of the dynamic of the labor force. And something that I wanted to show here is that in principle, with the classical von Bertalanffy model, if the initial condition, which is L of 0, is greater than is greater than the carrying capacity, okay, we have that the population starts to decay and goes up to the limit, which is lower than the initial condition. Here, in this case, we have the same situation, but the thing that, something that happens is that instead of seeing a decay in the population, we see an increment in the population. And this happens because the ratio between R1 and R2 is much more bigger. In particular, the difference between R1 and R2 is much more bigger. So this means that the new carrying capacity, which is the ratio between R1 and R2 times L infinity, actually is greater than the initial condition. So the system is pushed to increase the population up to reaching the limit. But as long as R2 increases, we can appreciate the opposite trend, because here the initial condition is above the limit actually. And this is still the constant parameter model. Here we have much more parameters to choose, because what we model here is the capital intensity, so the ratio between capital and labor force. As you can see here, we have an increasing function, even if we can choose different values for the parameters, but because clearly we have a bounded population dynamic, bounded labor force. So since we are modeling a ratio between capital and labor, capital becomes much more important in the long run rather than labor force. And in the end, this is the second model, so the time variant parameter model. And something that we see here, first of all, is that if you increase the frequency and the amplitude, we can appreciate that the seasonal pattern of our population dynamics. And again, we appreciate also the same feature as before, which is even if the initial condition is higher than the theoretical carrying capacity, we have that the population actually increases rather than decreases, okay? Because again, here the difference between R1 and R2 is much more bigger. But as long as R2 increases, we can see the same feature that we have seen before. And so this is consistent between the two models. And in the end, what we've done is to show I chose two comparative plots for the numerical solution and the bounding solutions. In particular, the blue line is the upper bound, so the exact solution that is computed inserting the maximum value of the function little g, while the orange one is the minimum, the lower bound for the solution, and the green line is the numerical solution that lies between the two lines. And this happens also for another set of parameters. Here, clearly the parameter changes, but we can appreciate the same feature. So the numerical solution is actually contained inside, and the theoretical solution is actually contained inside the bounds. So in the end, what we've done is to consider two extensions of the von Bertalanffy equation, and we insert inside the neoclassical growth theory model. And for the first case, we were able to find an exact solution, while for the second case, we were able to find an upper and a lower bound. And we tested with Mathematica, considering if the numerical solution displays this feature of being inside the limits. And so for future work, what we will consider is some empirical applications, so testing our model also with data, and also to extend this analysis, considering also other type of models related to population that displays the same feature of the von Bertalanffy, so that they consider a bounded population, but a little bit enriched. So this is a short bibliography of the model of our work, and thank you very much for your attention. If you want, you can download the material. It is attached to the link, and if you have any other question after suggestion after the conference, you can also write to me. There is all the email, all the contact details inside my profile. For instance, in answering to the question, what sector do you anticipate first, including the multi-sector version you mentioned for future work? For instance, as I said, von Bertalanffy equation is very used, for instance, in biology or other applied sciences in order to model cancer type evolution of cells. And so we are also working on this type of work, so not just working on the economic model, but considering the population dynamic, and to make some more to be more sound about this evolution